Welcome back, everyone, to the online Gas and Matroids seminar. Today, we're happy to have Kristyna Pekárková from Masaryk University. So, whenever you're ready, Kristyna.
Okay, thanks, and thanks for inviting me to this seminar. So in my talk, I would like to tell you something about the connection between Matroid parameters and integer programming. So before I start the talk, let me just mention that this is based on the results of joint work together with Marcin Bianski, Timothy Chen, Jay Cooper, Martin Kotecký, Dan Král, and Felix Schroeder. So as I said, the central topic of my talk will be integer programming. So I would like to start by recalling the problem, and rather than just jumping straight to the formal definition, I would like to start by a simple example, and that will be a variation of the well-known knapsack problem. So in the knapsack problem, I'm given a set of items, and each of them is assigned some weight and a priority. And in this talk, I will assume this will all be integers. And I also have a backpack, which has a certain weight limit. Let's call it big W. And the question in this problem is, what subset of items should I take so the weight limit is satisfied, and at the same time, the sum of the priorities of the items that I take is maximized. And if I wanted to express this as a very simple integer program, I could do something like this. So for each of the items, I would have a variable x1 up to xn. And since I have only two options, either I take each item or leave it, I will look for an assignment of zeros and ones to these variables, such at the same time the weight constraint is satisfied, so the sum of the weights for the items is less than this big W, and at the same time I want to maximize the priority, so I want to maximize this function, the sum of the priorities, with respect to this constraint. So this is an example of a very simple integer program, and in general, I don't need to have just one constraint. I could add, for example, some additional cost or volume. And typically, I would view this in a matrix form. So if I will talk about instances of integer programming, I will focus on the view of it as a matrix form. So I will have a matrix called a constraint matrix, some vector of variables x1 up to xn, for which I want to have integer values, and the corresponding vector on the right hand side. Yeah, and in the standard form, we consider the integer programming the following problem. So I'm actually given the constraint in the form of linear equations, and I want to minimize a function, so-called objective function, with respect to this to these constraints. So even though I mentioned like examples with inequalities and maximization, I can always transform any integer program to this form where I want to minimize, and the constraints are form of inequalities, or sorry, equalities. So integer programming is a fundamental problem of discrete optimization, and it is both of practical and theoretical importance. For example, I can find its notable applications in scheduling or planning, or string algorithms, or computational social choice. These would be problems such as voting and bribing. But the trouble with integer programming is that it's NP hard in general. So we actually don't know how to solve efficiently the instances of IP in general, and it's not easy to solve it even in cases when, for example, this objective function f is constant, and the constraint matrix contains only zeros and one. And the good news is that there exist some cases for which we know how to solve IP efficiently, and I would like to mention a few of the prominent classes. So the first class I would like to start with is IP in fixed dimension. So when I fix the number of variables of the instance, let's say it will be at most k, and then due to the famous result of Lester, I can solve integer programming in polynomial time. In a time bounded by this function. And in general, algorithms whose running time is in this form, as I will explain in more detail in a second, are called FPT algorithms. So this is a notion central to the area of parameterized complexity. So as you know, in classical complexity, I measure the complexity of the algorithm as the function of the size of the input. In parameterized complexity, I also consider some additional parameters, some additional info about the input, and I will represent this by this parameter k. And then this FPT algorithm is an algorithm whose running time can be expressed as some function of k times n to c, where so k is the parameter, n is the size of the input, and c as some constant which needs to be independent on this k. And so this is the idea that for every fixed k, I obtain a polynomial time algorithm. And for now, when I will say in the presentation that something is efficiently solvable, then I will mean that actually it belongs to this FPT class, which is sort of the analog of the P class in the parameterized complexity setting. And recent results in integer programming and parameterized complexity suggest or show that we can solve integer programming instances efficiently when the input instance or the constraint matrix has some kind of block-like structure. So here I have a short overview of some classes, some prominent classes that have been shown to be FPT quite recently and that have this kind of block-like structure. So the first case that I could mention is the n-fold integer programming, which looks like this. And so here the blue squares represent submatrices where I have non-zero values. The white space are just zeros. The second case here in the middle is two-stage stochastic integer programming, which essentially corresponds to a situation when I have some set of global variables that are common to all the rows, and after I set the values to these variables, these will be the columns on the left, then suddenly the original problem decomposes into a set of smaller independent subproblems. And the interesting thing here is that even though this n-fold and two-stage look kind of similar, the current results show or imply that to solve this two-stage stochastic is actually much harder than to solve these instances of n-fold. And the third case that I have here is so-called multi-stage stochastic integer programming, which is then the generalization of the two-stage. So again, I'm in a situation when I have a set of some variables, global variables, in the columns on the left. After I remove them, I suddenly decompose the problem into subproblems, but now in the multi-stage, I allow the subproblems further to have some kind of recursive or tree-like structure. And then the number of stages here is then the depth of the recursion that I allow the subproblems to have. And it turns out that this property of a matrix to have this kind of tree-like recursive structure can be further generalized and studied if we look at the corresponding graph to the matrix. So first, I would like to tell you about some options how I can view my graph, my matrix as a graph, and then what is the parameter that measures both the sparsity of the graph and the matrix. So if I have one of the options that I can obtain a graph from my matrix is so-called primal graph. So in this case, the vertices will correspond to columns, and the vertices in the graph will be adjacent if there exists a row in my matrix such that the corresponding entries are non-zero. It's easy to see on this picture. So for example, for the first column, I have the yellow vertex in the graph. Second is the orange. And if I look at the matrix, I can see that there is the fourth row where the yellow and orange entries are non-zero. So this will mean that the yellow and orange vertex will be connected by an edge in my graph. On the other hand, I cannot see any row in which I would have a yellow and pink non-zero entry. So this will mean that this two vertices, this yellow and the pink corresponding to first and third column, will not be adjacent in the graph. Another way how I can look on the matrix as a graph is the dual graph. This is defined in the same way as primal, except here the vertices will correspond to rows, and two vertices will be connected by an edge if there is a column such the corresponding coefficients are non-zero. And for completeness, let me just mention there is also another way that I could express this, and it will be the incidence graph of a matrix that will be a bipartite graph in which one part would correspond to, or would be vertices corresponding to the rows of the matrix, the other by columns, and then two vertices of the row and column will be connected by an edge if the particular entry is non-zero. So this is a way how I can view my matrix as a graph. And then I somehow want to measure the sparsity both of the graph and the matrix. And it turned out that the notion that allows us to do this, or that's very useful in the context of integer programming, is the notion of tree depth. So I assume some of you may have heard about the notion of tree width, which is one of the most prominent parameters in structural graph theory. And tree width is a parameter that tells me how close my graph is to a tree. So it's a number, and the lower the number, the closer it's to a tree. And tree depth is something very similar. It's a parameter that tells me or measures how close my graph is to a tree of small depth, so a star. And formally it's defined as follows, and it's defined via decomposition. For this, I need the notion of closure. So if I have a rooted tree, then I can obtain its closure in this way. So I take each vertex and add an edge to every its ancestor. So in this picture, it will be the red edges that will be the closure. And then the tree depth of a graph would be the minimum height of rooted forest, such that the closure of the rooted forest contains the graph G as a subgraph. Yeah, so in this picture, this will be the graph G on the left. I'm not sure whether you can see the mouse like pointing on it. Yeah, in this picture, the red lines is the closure of the rooted tree, and then these thick blue lines should visualize how I can find this graph G there as a subgraph in the closure. So this is tree depth of graphs, and then I can easily extend this notion to matrices, because I will simplify the primal tree depth of matrix to be the tree depth of its primal graph, and in analogous way, the dual tree depth and the primal and incidence tree depth would be the tree depth of the corresponding graphs. And it turned out that tree depth is a parameter turned out to be a very important tool in the design of algorithms for solving IP, because it allows me to encode the instance in kind of tree-like structure and then solve it efficiently. And this has been formalized by this result of Kotetski, Levin, and on, who showed that we can actually solve integer programming efficiently when the constraint matrix has small primal or dual tree depth and also small entry complexity. So I will mostly focus on the notion of tree depth, but let me just mention here that the entry complexity is the largest size of a binary encoding of an entry of the matrix. However, this parameterization by the tree depth, primal and dual, has a certain disadvantage, which is something that I would like to illustrate on the following slides, together with the motivation for our research and the main questions that we were interested in. So imagine I give you the following task to solve a system AX equal to B, where A is some constraint matrix, some integer matrix, X is the vector of variables, and B is the vector on the right-hand side. And together with this task, I also give you a choice whether you would want to solve this system with the matrix on the left or the one on the right, and they are row equivalent. So given this choice, I assume most of you would choose the one on the right, simply because it has a nicer structure, more zeros, and we would expect that it would take us less time to solve it than the ugly matrix on the left. And a similar thing goes for integer programming and integer programming solvers. So let's look at the corresponding primal graphs and tree depth of these two matrices. So for the matrix, for the dense matrix on the left, the primal graph in this case would be the complete graph in 6 vertices. And in this case, I cannot do anything else than just as the decomposition to take a path on 6 vertices and take its closure. So in this case, the tree depth would be 6. On the other hand, to the matrix on the right, if I look at the primal graph, I obtain something much sparser. And in the case, this tree depth would be 3. But at the beginning, I told you that these two matrices were row equivalent, which means that tree depth as a parameter has the disadvantage that it's not invariant under row operations if I define tree depth on matrices. So what can happen with the integer programming solvers is that they cannot be, for example, even applicable on some matrix that is not sparse itself, but might be equivalent to another sparse form with small tree depth. And this led us to two main questions we are interested in. So the first one is, if I give you a matrix. First of all, can you tell me whether there exists some row equivalent sparse form? And the other question, okay, so if you can decide this, can you also transform the input matrix to this row equivalent sparser form? Can you find the row operations that you should perform on the input so that you get something on which the algorithms may run faster, better? And this process of transforming a matrix to its kind of row equivalent sparser and in some sense more computationally tractable form is called a preconditioner. So what we are interested in is the existence and efficient computability of these preconditions, these transforming operations. And so here is the place where matrix theory comes to play. So to answer these questions about the preconditions, we used some properties of certain depth parameters of matroids, which I would like to introduce in the following slides. So I would like to just here recall the definition. I'm not sure whether it's needed. I would like to recall here the definition of matroid deletion and contractions, because these will be the operations on which the parameters will be based on. So in the deletion, so if my ground set of the matroid will be x, then by deleting x prime for it, the ground set changes to x minus x prime, and the new set x double prime will be independent in the small matroid if it was independent in the original matroid. And contraction, if I want to contract a matroid by x prime, then again the ground set changes to x minus x prime, and the set in the new matroid, so x double prime, will be independent if the rank of x double prime union x prime will be equal to the size of x double prime plus rank of x prime. So for me, in the rest of the talk, I will mostly work with f represented matroids, and in this case, the contraction then corresponds or can be expressed by the notion of quotient space or factoring along the span of the x prime. And with these notions, I would like to move to these to the parameters that we use to answer the questions about the preconditioners. And the first of them will be the deletion depth, which is actually first defined in the work of Devospan and Ohm. And I think before it was also studied in the context of graphs under the name D-type by Robertson and Seymour. And it's defined recursively as follows. So if my matroid contains just a single element, then the deletion depth is 1. If the matroid is disconnected, then as the deletion depth, I will take the maximum deletion depth of the components. And in the third case, if it's connected, then I will take the minimum deletion depth of a matroid minus some element of E, increased by 1, and the minimum will be taken over all elements of the matroid. And this procedure, this process of deleting the elements can be also visualized by a notion of deletion decomposition tree. So first, I have here the formal definition, and I would like to illustrate this on a concrete example. So the deletion decomposition tree will be constructed as follows. So if my matroid has one element, then the tree will be just a single vertex labeled by this element. If the matroid is not connected, and then I will take the decompositions for the components and identify the roots. And in the third case, when the matroid is connected, I will find an element such after the deletion of this element, the deletion that decreases, I will take the decomposition of the small matroid and attach it to a new root, and moreover label the connecting edge by the deleted element. So I think it will be easy to see on the following example. So I will have this graphic matroid, and I would like to construct the deletion decomposition for it. So I will start deleting the edges. In this case, it's connected, so I want to split it into components, and I will start by deleting the edge A. So this will split it, the matroid, into 2 connected components, and again within them I would like to split it, so I will delete the edge B and C. And this way I will split it actually to 4 single element matrices. So here is the whole sequence again. just important parts or steps for which I will need for constructing the decomposition, and I will start constructing it from the bottom. So I will start with these 4 single element matroids. And according to the definition, so for each of them, I will create a vertex and label it by the element. Now, if I move one step back, then I will take within each of these parts, so D and E and F and G, I will take the decompositions and merge them together to one root. In the third step, so I was deleting the edge, so that was the third line in the definition. So I will take the decompositions of the components and create a new root and attach it to the decomposition, and moreover label the edge by the deleted components, so B and C. In the fourth step, again, I will take the decompositions for these components, this small trees, and I will identify their roots together. So I obtain a decomposition of height 2. And in the final step, again, since I was deleting this edge A here, I will create a new root and attach it to the already obtained decomposition and label it by this edge A. Yeah. So this is the way how I could obtain this simple deletion decomposition tree of this matroid. And then the height of this decomposition tree is then the deletion depth of the matroid. In the rest of the talk, or towards the end of the talk, I will also consider decompositions that might not be optimal, in the sense that they will not have the smallest depth or height possible, but will be constructed according to the rules in the definition of deletion depth. The other parameter that I would like to mention here is contraction depth, which is defined in the same way as deletion depth. And just in this case, I'm not deleting elements, but I'm contracting the elements of the matroid. And finally, I would like to mention or define the parameter of contraction star depth, which was first defined and studied in the work of Kadosh, Králi, Benau, and Mach. It was sort of introduced as the analog of the tree depth in the matroid setting. And I would like to mention that it was originally introduced under the name branch depth, but at the same time there was another parameter of the same name introduced in the work of Devos, Kohn, and Ohm. So in our work, we further decided to rename it to contraction star depth and use this name. So here I first have the definition for F represented matroids. And this definition also nicely illustrates why we choose this name, this contraction star depth. So in the case again, it's a recursive definition, and if my matroid has a single element, then the contraction star depth of the matroid will be 0. In the case if disconnected, I will take the maximum contraction star depth across the component. And in the third case, it will be the 1 plus the minimum contraction star depth of a matroid that we obtain by factoring along an arbitrary one-dimensional subspace. So it was that contraction star depth, since in this definition we allow contraction by an arbitrary one-dimensional subspace, not like in the case of contraction depth, where it was just subspace generated by an element of E. So it turns out that this contraction star depth is more general than contraction depth. And it will always be less than or equal than the contraction depth of the matroid.
Sorry, can I ask a question?
Yeah.
When you do this contraction star depth, you potentially are adding a new element and contracting it out. Is that right? Sorry,
I just couldn't hear it.
Are you adding a new element? The element K might be a new element. It's not actually in the matroid.
No, you're not adding it. I mean, the ground set, I think it will stay the same.
So how is this different from just contracting a single element?
Because in a sense, it might help me.
So I do something that supervisor should not do when a student is giving a talk. So another way of thinking of this is adding an element and contracting it.
Oh, yeah, that's okay. So that's what I thought. So you're doing a quite You're doing
Yeah,
a quotient, right?
Yeah, so basically in the representation, you quotient according to an arbitrary space, which was not originally generated by an element, which is of course equivalent to adding an element and immediately contracting it.
Yep. Okay, good. Understand. Thanks.
Yeah, okay, thanks. This was the definition for F-represented matroids, and the general definition is then as follows, is defined by a certain decomposition tree. So for me, the contraction startup decomposition will be a pair where T will be a rooted tree with exactly a number of edges equal to the rank of the matroid, and F will be a mapping which maps the elements of the matroid to the leaves of the tree in the following way. So if I take any subset of the elements of the matroid and look at the subtree induced by this image, then it needs to hold that this tree has at least the rank of X prime edges. Yeah. So for example, I will have this this binary matroid. Its rank should be 5. So here's an example of a contraction start decomposition. It needs to have 5 edges in total. And if I, for example, look at this node or this leaf, then the rank of the set of these elements will be 2. So it needs to hold it for this path from the leaf to the root. There needs to be at least 2 edges. Yeah. And then so every matroid would have a trivial contraction start decomposition, because what I could do, I could just take a path of length equal to the rank of the matroid, take one end vertex as the root, and map all the elements to the others by its mapping F. So the contraction startup is always at most the rank of the matroid. And for me, by decomposition definition stands as follows. So for me, I will consider the contraction startup to be the minimal height of a contraction startup decomposition. So these are the parameters that I would like to mention. And before I actually move to the result itself, I would like to show here a brief overview of the parameters, kind of the hierarchy, and also mention the key property of the parameters, why they were useful for us and why they helped us to solve these questions about preconditioners. So here in this kind of diagram, it should visualize the parameter in this way. So on the top, I have these parameters that are the most general. So for example, the branch rate will always be smaller than contraction start depth and contraction deletion depth of matroid. And the key property that I would like to mention is the following one. So the question that interested us, what was the disadvantage of T-depth? It was the disadvantage that is not invariant under operations. And given a matrix, I was interested in the question whether there exists some row equivalent sparsiform with small T-depth. So the question is, what would actually be the optimal or the smallest T-depth of all row equivalent matrices? And the property of this parameter is that because if I have a matrix and if I perform row operations on it, then I don't change the linear independence of the column vectors. So it will mean that the matrix of all row equivalent matrices will be the same. And also it turns out that all the parameters here, and the contraction startup and contraction depth, deletion depth will be the same for all row equivalent matrices. So it turns out that these parameters are invariant under row operations. Now I would like to mention finally the results. Before I define these parameters for matroids, if I will speak about deletion depth and contraction depth of the matrix in the context of matrices, then I will mean that is the corresponding parameter of the sorry, there should be column matroid. Yeah, the vector matrix formed by the columns of A. And the first result here is the characterization of the optimal dual tree depth. So this TD star here will mean for me, or we define the smallest dual tree depth of all row equivalent matrices. And what we did, we showed that this TD star is smallest, the optimal dual tree depth is in fact equal to the contraction star depth of the matroid, yeah, or of the matrix. The second result, so we kind of extended this characterization also to to the primal tree depth and the incidence tree depth of the matrix. So here the optimum or the minimal primal tree depth is equal to the deletion depth of the matrix, and in the case of incidence tree depth, it's equal to the contraction star deletion depth of the matrix plus 1. And based on the structural results, we were able to answer the second question, and it was the construction of the preconditionals for the matrix sparsity. So first we answered the question for a dual tree depth. So here we developed the parameterized algorithm that given a rational matrix, not just integer but rational matrix, and an integer d and e, such that the entire complexity of the matrix is bounded by the integer d. So the algorithm either tells me, no, there's no row equivalent matrix such that the tree depth will be smaller than d, or it actually outputs a row equivalent matrix with the minimum dual tree depth possible. So here the important thing is that also the coefficients are bounded, which is also important for the integer programming solvers. And I would like to give here a very high level overview of how the algorithm works. So core of the algorithm is computing the contraction startup decomposition of F represented matroids. But if you look at the theorem here, I mentioned that I would like the algorithm to work for rational matrices. So the first thing that what we do here is given a matroid, representation of a matroid over rationals, we run an algorithm that outputs another representation of a matroid over some finite field, and will hold that these two representations or these two matroids will be isomorphic in the case that the matrix has small dual tree depth, so or there exists a row equivalent matrix of small dual tree depth. So after this, we computed the contraction startup decomposition for this representation over a finite field, and that starts by an approximation algorithm that follows from the work of Kadosh et al., which computes contraction startup decomposition of depth at most 4 to the contraction start depth of the matroid. And then when we do that using dynamic programming, we kind of travel through this decomposition from left to right and compute like the partial kind of trees, parts of the trees called frontiers. And then when arrive back at the end of the tree, if it was successful, we just end with one element and backtrack and kind of glue the parts of the tree together to obtain the decomposition of optimal height. And then finally, using the information that is stored either in the leaves of the decomposition or labels of the edges, we construct the matrix of minimum dual tree depth possible that is row equivalent to the output. And the other algorithm, or the second algorithm that I would like to mention here is the precondition for small primal tree depth. So again, a parameterized algorithm that given an rational matrix E and integers D and E, such that the entry complexity is bounded by E, it outputs a row equivalent matrix whose tree depth is primal tree depth is at most D, and the entry complexity is bounded by a function of D and E. And here the approach is a bit different. So again, the core is computing here, in this case, the deletion of decomposition. But we do this in a different way. So again, at the beginning, there's this step in which we, for a matroid, for a representation of the matroid of rationals, we compute a representation over finite field. So again, it will hold that these two matroids will be isomorphic if the deletion depth of the matrix and the matrix is small. And then on this, we compute a decomposition, and this is based on MSO model checking. So from the results of Hliněný, follows that we can solve MSO model checking efficiently on matrix of bounded branch width, that is an FPT. And since branch depth of a matroid is always less than or equal to the deletion depth of a matroid, and also the property that deletion depth of a matroid is at most D is definable in monadic second order logic, it follows that there's an algorithm for checking whether the deletion depth of the matrix is an FPT. And then what we did, we extended this algorithm for checking whether the deletion depth is at most D to algorithm that constructs the decomposition tree in a recursive way, analogous to the way that I showed you in the example. So in case there's one element, I create the one vertex decomposition. In the case the matroid is disconnected, I first identify the components, which I can do in polynomial time in the Oracle model. And then I proceed recursively. And when I obtain the decompositions for the components, I can merge the roots. And in the other case, when the matroid will be connected, then I would just iterate over the elements and find the elements which after the deletion of this, the deletion depth of the matroid will decrease. And again, proceed recursively with the smaller matroid, obtain the decomposition. And with this, I would like to move to the last part here, and that is related open problems to our result. So first of all, what we would like to do is improve the sparsification algorithms. So the first algorithm that I was describing was the algorithm for computing matrix of small dual tree depth. And it started with the approximation algorithm of Kadosh et al. However, this algorithm outputs a decomposition of the at most 4 to the contraction startup of the matroid, which is not ideal. So we would like to speed up this algorithm and develop actually a constant factor approximation algorithm for computing the contraction startup, which would then also improve the running time of the preconditioner quite significantly. The other problem is improving the other preconditioner, so the preconditioner for computing matrix of small primal T-depth that was based on the model checking. So what we would like to do here is actually replace the model checking approach with a more direct combinatorial and dynamic programming based approach, similar to the case of the preconditioner for computing small dual tree depth. And the third problem that I would like to mention here is the characterization of matrices with bounded infinite norm of the Graver basis, and also finding the connection of the matroid parameters, the parameters to the Graver basis of integer matrices. I'd like to explain here a bit or tell something more about the notion of Graver basis. So for integer programming, in general, we distinguish two main research directions. So either there's the fixed dimension, where was the algorithm by Lenstra, or variable dimension. So the algorithms that try to solve IP in fixed dimension, they often rely on arguments from discrete geometry, while the algorithms for solving IP in variable dimension rely on algebraic arguments and dynamic programming approach. And a lot of these algorithms for solving IP in variable dimension are based on the notion or the framework of so-called iterative augmentation, which is a concept that is sort of similar to computing, for example, maximal flows on graphs. So the process of solving IP via iterative augmentation means that you start with some initial feasible solution to the IP, and then you iteratively apply some improving steps until you converge to the optimal solution. And the Graver basis here essentially represents the set of these improving steps that I can apply to the feasible solution to converge to the optimal. So it's some set of vectors defined over the integer kernel of a matrix. And it holds that for every integer matrix, this Graver basis will be a finite set, but unfortunately, it can be also very, very large, exponential in the size of the number of the columns of the matrix. So we would like to somehow avoid the computation and of the whole Graver basis of the matrix, and this can be actually avoided if we study the norms of the elements of the vectors of the Graver basis. So either the L1 norm of the vectors in the Graver basis or the L infinity norm. Yeah, and so determining the bounds for for the L1 infinity norm is one of the kind of most important questions in the area of optimization and parameterized complexity, because often these bounds represent the leading terms in the running time of the algorithms for solving IP with the iterative augmentation. And what we'd like to do is somehow characterize when a matrix has bounded L1 or infinity norm using the parameters of the column matroid. And for the L infinity norm, we have the partial results. So we actually characterize that a matrix has small L1 norm. Sorry, the gravity basis of the matrix has small L1 norm. If the matrix has small contraction depth, so in the case when there exists a row equivalent matrix of small dual tree depth. However, we still don't know the characterization for the L infinity norm. So the open problem here is to find a suitable parameter, matroid parameter that would characterize the property of the matrix to have bounded L infinity norm of the elements of the gravity basis. And with this, I would like to thank you for your attention and conclude my talk.
Okay. So on the count of three, let's all unmute and give Kristyna a round of applause. 1, 2, 3. Okay, and are there any questions?
I've got a question. Can you say something about the process for finding a representation over a finite field at the beginning of your algorithm?
Yeah. So I think here in this case, it is based on the fact that I can. So I think it works with the fact that I can. The algorithm for computing the primal TDEP. So here it works on the bound. So if I have a matrix of bounded primal TDEP and the complexity, I can also bound the entries of the circuits of the matrix, and I can actually use this bound on the entries of the circuits to find this prime for the FP field, such that sorry, I think I got lost in this. I need to find a sufficiently large prime for this field, and this is based on the bound on the circuit entries of matrices with bounded tree-dependent complexity.
So do you get something that is significantly better than just, say, upper bounding all the determinants and choosing a prime that's bigger than all of them? I'm wondering how big the field is as a function of the tree depth, for instance, deletion depth, sorry.
Yeah, in this case of the deletion depth, I'm not sure. In this case, I think it would be at least double exponential in this.
Okay, thanks.
Any other questions? Kristyna, would you mind going back to the slide with your first main result about dual tree depth and contraction star?
This one, yeah.
So is this just for matrices over the rationals, or does this also hold for matrices over finite fields?
So I believe we have this for rational matrices.
And kind of a weirder question. So can you always find a choice of A prime that has an identity submatrix, or at least a submatrix where it's the identity matrix after scaling columns? Or is that too much to ask for?
So, sir, could you please, you're looking for a row equivalent form in which?
Yeah, row equivalent
Mhm.
form that has an identity submatrix after possibly scaling columns as well.
Yeah, I think what we do especially in this algorithm, that in the end, like after computing this decomposition, always process this original matrix, in which I think there will be an identity matrix from the columns.
Other questions? Okay, maybe I'll stop the recording and we can continue with some informal discussion.